view of Earth. Our objective in these 2 lectures is to recall some of the basic notions of the Earth sciences, especially the Earth's composition, and to introduce seismic waves, which allow us to understand the solid Earth's interior before we turn to the key topics of this series, which are earthquakes and volcanoes, energy resources, and climate change. Let's start with some learning objectives. We'll be familiarizing you with the average temperature of the Earth's surface, the average ocean depth, and the percentage of the Earth's surface occupied by oceans. You'll familiarize yourself with the notions of photosynthesis, precipitation, evaporation, and the deep biosphere. You will learn about the differences between continental and oceanic crusts. You will also learn about the differences between inner and outer cores. Let's start with the view of the Earth from space through the Apollo program, or more precisely, Apollo 17. Taking a full photograph of Earth from space takes some doing. In 1972, the crew of Apollo 17 took a camera to the moon in order to bring the full sphere into view. At a time when our planet is undergoing critically important changes, this type of global view offers vitally important information about how Earth is changing. Notice Saharan dry land, the wetted sub-Saharan. The water is almost everywhere on Earth, including oceans and glacial ices. Another view of the Earth showing the 7 continents, including Africa, Antarctica, Asia, Australia, Europe, North America, and South America. And it also shows the 5 oceans: the Antarctic Ocean, the Arctic Ocean, the Atlantic Ocean, the Indian Ocean, and the Pacific Ocean. A close look at the Earth's surface shows that 61% of the northern hemisphere is covered by water, while 81% of the southern hemisphere is covered by water. However, on a planetary scale, the ocean is small. In fact, there is more water within the Earth's interior than in its oceans and atmosphere. A schematic illustration of the relative heights of the major features of the Earth's surface. The horizontal axis, labeled the percentage of Earth's surface, gives the percentage, while the vertical axis shows elevation above or below sea level. Sea level is the mean sea level, which is an average level of the surface of Earth's oceans. This illustration also shows the Earth has 2 types of crust: continental and oceanic crust. Note that Earth's surface is not flat. It has topography. Ignoring oceans, Earth's surface is dominated by 2 distinct elevations. Most land is 0 to 2 kilometers above sea level, and most of the sea floor is 3 to 5 kilometers below sea level. As we go through this series of lectures, it is important that you refamiliarize yourself with the major features of the Earth's surface, namely the 7 continents: Africa, Antarctica, Asia, Australia, Europe, North America, and South America, as well as the 5 oceans. including the Antarctic Ocean, the Arctic Ocean, the Atlantic Ocean, the Indian Ocean, and the Pacific Ocean. The major mountains are also included: the Himalayan mountains in Asia, the Alps in Europe, the Andes in South America, the Rockies and Mount St. Helens in North America, Mount Pinatubo in the Philippines, and Mount Kea and Mount Loa in Hawaii of the Earth's surface. The average land elevation is 840 meters. Other useful statistics to keep in mind are the average ocean depth is 3,800 meters. The average ocean temperature is 3.9 degrees Celsius. And the average global temperature is 14.6 degrees Celsius. About 50% of the Earth's population lives less than 240 kilometers from an ocean. In Japan, by contrast, 96% of the population lives less than 100 kilometers from the ocean. We generally divide the Earth into 4 spheres. 1, the atmosphere. 2, the hydrosphere. 3, the biosphere. And 4, the lithosphere. The atmosphere is a thin gaseous envelope surrounding Earth. The hydrosphere is water, primarily the oceans. The biosphere includes all living things on the planet. The lithosphere is the rocky outer shell of the Earth. All these spheres, the lithosphere, the hydrosphere, the atmosphere, and the biosphere, are linked through flows of mass, energy, and life. Their interactions have affected the development of our planet. Solar energy is essential to the function of each of these spheres and for the entire system. Let me reiterate. All parts of the Earth system, the lithosphere, hydrosphere, atmosphere, and biosphere, are linked. They're linked through flows of mass, energy, and life. Interactions between these realms have affected the development and evolution of our planet. Note that the word cryosphere is often used to describe the frozen water in the Earth's system and includes frozen parts of the oceans, such as the waters surrounding the Antarctica and the Arctic, which is here considered part of the hydrosphere. Let us now describe in a little more detail the atmosphere, hydrosphere, biosphere, and lithosphere. The atmosphere is unique in the solar system. Why? Because it provides the air we breathe and protects us from the sun's intense heat. It is thin and tenuous. It is composed of 78% nitrogen, 21% oxygen, and minor amounts of carbon dioxide, argon, and water vapor. In other words, 2 gases, nitrogen and oxygen, represent 99% of the gases in the atmosphere. Note that billions of years ago, in the early atmosphere, oxygen was not present, and therefore there was no life as we know it today. The photosynthesis of plants put the oxygen there. More remarkably, photosynthesis of plants put oxygen in the atmosphere at the right percentage, 21%. Why not less? This is a complex process. By the way, photosynthesis is a process used by plants and other organisms to convert light energy, normally from the sun, into chemical energy that can later release to fuel the organism's activities. Photosynthesis began 3.5 to 2.5 billion years ago. Again, it produced oxygen and removed carbon dioxide and methane, also called greenhouse gases, from the atmosphere. The atmosphere is generally divided into different layers. The ground is shown in dark brown at the bottom of this picture. The approximate altitude in kilometers is given on the right-hand scale. The approximation here is due to the fact that the actual altitudes of the layer boundaries vary with the Earth's surface topography. We cannot expect these boundaries to have the same altitudes above the peak of the Himalayas and above the sea level. The peak of the Himalayas is about 8 kilometers above the sea level. The temperature is shown in the horizontal axis. Let's now briefly describe the different layers of the atmosphere. We'll start with the troposphere. This is the lowest atmospheric layer. It is about 11 kilometers thick. Most clouds and weather are found in the troposphere. The troposphere is thinner at the poles, averaging about 8 kilometers thick, and thicker at the equator, averaging about 16 kilometers thick. The temperature in the troposphere decreases with altitude. Next, we'll talk about the stratosphere. The stratosphere is found from 11 to 48 kilometers above the Earth's surface. This region of the atmosphere contains the ozone layer, which absorbs most of the harmful ultraviolet radiation from the sun. The temperature increases slightly with altitude in the stratosphere. The highest temperature in this region is about 32 degrees Fahrenheit, or 0 degrees Celsius. Now we'll move to the mesosphere. The mesosphere is obviously above the stratosphere. Here, the atmosphere is very thin, and the temperature is decreasing with altitude, about negative 130 degrees Fahrenheit, or negative 90 degrees Celsius at the top of the mesosphere. Now let's talk about the thermosphere. The thermosphere starts at about 55 kilometers. The temperature is quite high. Note that here, temperature is not measured using a thermometer, but by looking at the motion and speed of the rarefied gases in this region, which are very energetic but would not affect a thermometer. Temperatures in this region may be as high as thousands of degrees Celsius. The exosphere is the region beyond the thermosphere, and the ionosphere overlaps the other atmospheric layers from above the Earth. The air is ionized by the sun's ultraviolet light. These ionized layers affect the transmittance and reflectance of radio waves. We will discuss this issue in the climate change classes. In addition to Earth, many of the other planets in the solar system have atmospheres, including Mars and Venus. Venus's atmosphere is composed mostly of carbon dioxide. The Martian atmosphere is also composed mainly of carbon dioxide, with some nitrogen and argon. Again, Venus's atmosphere is composed mostly of carbon dioxide. It contains minor amounts of nitrogen and other trace elements, including compounds based on hydrogen, nitrogen, sulfur, carbon, and oxygen. Though the atmosphere of Venus is shallower than the Earth's atmosphere, it is much hotter and denser than that of Earth. As greenhouse gases, or carbon dioxide and methane, warm a lower atmosphere, they cool the upper atmosphere, leading to a compact thermosphere. Based on the temperature profile of Venus's atmosphere, shown here, we can see that Venus has no stratosphere. Its troposphere extends to an altitude of 65 kilometers, an altitude at which the mesosphere has already reached on the Earth. At the top of the troposphere, temperature and pressure reach Earth-like levels. The Martian atmosphere is very thin and composed mainly of carbon dioxide, with some nitrogen and argon. The thin atmosphere also increases the variability of the planet's temperature. Mars' surface temperatures vary from lows of approximately negative 140 degrees Celsius or negative 220 degrees Fahrenheit during the polar winters to highs of up to 20 degrees Celsius or 70 degrees Fahrenheit in the summers. Note that the study of extraterrestrial atmospheres is useful because it allows us to gain more insight into Earth's atmosphere. Let's now move to another Earth sphere, the Hydrosphere. It is also known as the blue planet. It describes the total mass of water on or near the Earth's surface. Basically, water covers 71% of the Earth's surface. Therefore, you are more likely to find minerals that you may be looking for below the ocean rather than inland. Anyway, water covers 71% of the Earth's surface. From this amount of water, 97.5% is in the oceans, and 2.5% is found in glaciers, groundwater, lakes, and streams, or freshwater. In volume, the current estimations are that we have about 1,400 million cubic kilometers of water on Earth. This volume includes water in liquid and frozen forms in groundwater, glaciers, oceans, lakes, and streams. Salt water accounts for 97.5% of this amount. Freshwater accounts for only 2.5%. Yes, the amount of freshwater on Earth is small. Let's look at the partition of the 2.5% freshwater. Of this freshwater, 68.7% is in the form of ice and permanent snow covering in the Arctic, the Antarctic, and in the mountainous regions. Next, 29.9% exists as fresh groundwaters. Only 0.26% of the total amount of fresh water on planet Earth is easily accessible. It is found in lakes reservoirs, and river systems. Not only is the amount of fresh water on Earth small, the amount of accessible fresh water is tiny. Yes, water is everywhere on Earth. About 70% of the surface of the Earth is covered by water. Water is in the air, on land, between the rocks, and in every living thing. There are solids in the deep glaciers, liquids in the oceans, and the vapor state of clouds. While there might not be a lot of life in or on those glaciers, they will eventually melt. Once they melt, they start to affect all of the life on Earth. Again, all of the physical states of water are equally important because they are all connected. Let me recall some basic notions about water. Water, in its purest form, is the compound H2O. There are 2 hydrogen atoms bonded to 1 oxygen atom. Generally, you won't find pure water. There are usually other compounds, ions, or particles mixed with water. While water may move and carry other substances with it, remember that the small water molecules are the things that make life on Earth possible. Liquid water makes the Earth a special place. Our planet has a very nice temperature range that allows water to remain in a liquid state. If we were a colder place, like Pluto, all of the water would be permanently frozen and solid. On the other hand, if we were on a very hot planet, all of the water would be in a gas state. Water vapor and solid water are relatively useless to the organisms of Earth. Let's briefly discuss the hydrologic cycle, also known as the water cycle. The water cycle is a continuous cycle where water evaporates, travels into the air, and becomes part of a cloud. It then falls down to Earth as precipitation, and then evaporates again. This repeats again and again in a never-ending cycle. More precisely, the water cycle transfers water from one state or reservoir to another. Reservoirs include atmospheric moisture, oceans, rivers, lakes, groundwater, subterranean aquifers, polar ice caps, and saturated soil. Solar energy, in the form of heat and light or insolation, and gravity cause the transfer from one state to another over periods from hours to thousands of years. Most evaporation comes from the oceans and is returned to the Earth as snow or rain. Let me emphasize some of these points by quoting author Mark DeVille, who says, "On Earth, the total amount of water has almost certainly not changed since geological times. What we had then, we still have. Water can be polluted, abused, and misused, but it is neither created nor destroyed. It only migrates. There is no evidence that water vapor escapes into space." Every year, the turnover of water on Earth involves about 600,000 cubic kilometers of water. This is water that evaporates from the oceanic surface and from land. A similar amount of water falls as atmospheric precipitation. Again, 2 phenomena are involved: evaporation from oceans and land to atmosphere, and precipitation, from atmosphere to land and oceans. The difference between precipitation and evaporation from the land surface represents the total runoff of the Earth's rivers and direct groundwater runoff to the ocean. These are the principal sources of fresh water needed to support life and man's socioeconomic activities. For the clarity of this figure, let's define a couple of words. Evaporation. This occurs when the physical state of water is changed from a liquid state to a gaseous state. Condensation. Condensation is the process by which water vapor changes its physical state from a vapor, most commonly, to a liquid. Precipitation. Precipitation is the process that occurs when any and all forms of water particles fall from the atmosphere and reach the ground. Runoff. Runoff is flow from a drainage basin or watershed that appears in surface streams. Sublimation. Sublimation refers to evaporation from snow and ice. Transpiration. Transpiration refers to the expiration of water through the minute pores or stomata of trees. Evapotranspiration. Evapotranspiration is the term used by hydrologists in reference to the processes of transpiration, sublimation, and evaporation. Let us now turn to the biosphere. The biosphere includes all life on Earth, animals and plants on land, and in the sea and air. This includes tree roots, flying insects and birds, and much more. Notice that there is life in the ocean floor despite the fact that the pressure is extreme and there is no sunlight penetration. Yes, even deep under the terrestrial ground and the seafloor, life is very abundant, albeit mainly in the form of microorganisms which are not visible to the naked eye. In fact, the deep subsurface biosphere represents a substantial fraction of Earth's total biomass. First estimates suggest a contribution of 10 to 30%. It is amazing that life exists deep under the terrestrial ground. Let me recount a story to you. Jules Verne's book, A Journey to the Center of the Earth, reports how Professor Leidenbrock, his nephew Axel, and their guide Hans meet a versatile realm of living organisms on their descent into the interior of our planet. When the novel was first published in 1864, the idea of life existing in the deep subsurface, remote from sunlight and air, was genuinely science fiction. But towards the end of the 20th century, when scientific drilling opened the window into hundreds of meter-deep environments, it became clear that Jules Verne, in a sense, was right. By the way, biomass is the total weight of organic material of a particular species or in a particular habitat per unit of area or volume. In summary, the biosphere is the biological component of Earth's system. The biosphere includes all living organisms on Earth, together with the dead organic matter produced by them. The biosphere interacts with and exchanges matter and energy with the other spheres, helping to drive the global recycling of carbon, nitrogen, phosphorus, sulfur, and other elements. In other words, the physical properties of the biosphere in terms of its surface reflectance and exchange of heat and moisture with the atmosphere are also critical for understanding global circulation of heat and moisture, and therefore climate. Alterations in both the physics and chemistry of the Earth's systems by the biosphere are fundamental in understanding anthropogenic global warming. Actually, I have just summarized the climate change classes. Anthropogenic refers to the fact that the effects under consideration are of human origin. Anthropogenic is an important word in modern climate change studies. And, again, photosynthesis is a process used by plants and other organisms to convert light energy, normally from the sun, into chemical energy that can be later released to fuel the organism's activities. Photosynthesis began 3.5 to 2.5 billion years ago. It produced oxygen and removed carbon dioxide and methane, or greenhouse gases. Let's conclude this description of biosphere by returning to the deep biosphere. The discovery of the deep biosphere gives rise to new, fundamental questions about the evolution and distribution of life. Considering the broad range of temperatures and high pressures in the subsurface, and the lack of fresh organic matter as a source of energy and nutrients, the existence and survival of an extensive deep biosphere are remarkable. Geofuels, that is, gases that are generated by mineral water interactions or derived from the deep crust, might be an alternative energy source in the absence of light and photosynthesis. So far, only little is known about the individual inhabitants of the deep biosphere, about their genetic diversity, metabolic capabilities, and survival strategies. Moreover, the relationships between deep subsurface ecosystems and the surface world remain to be explored. Let's draw your attention to the coastal zone of the Red Sea and the Gulf of Aden. The region contains some of the world's unique coastal and marine environments in the Gulfs of Aqaba and Suez, the Red Sea, and the Gulf of Aden. Among the most notable is the extraordinary system of coral reefs and their associated animals and plants. Surrounded by arid terrestrial environments, which are themselves unique, these environments support rich biological communities and representatives of several endangered species. These natural resources have supported coastal populations for thousands of years and nourished the development of both a maritime and trading culture, linking Arabia and Africa with Europe and Asia. Let's take a 15-minute break. We will start the next session by answering these quizzes. Good luck. We're back. Let us start by answering the questions posed in the previous section. List and briefly describe the 4 spheres that constitute our environment. Here is the answer: atmosphere, hydrosphere, biosphere, and lithosphere. What is the amount of fresh water in volume that is available in the world? In volume, the current estimations are that we have about 1,400 million cubic kilometers of water on Earth. This volume includes water in liquid and frozen forms in groundwater, glaciers, oceans, lakes, and streams. Freshwater accounts for only 2.5%. Where is the Gulf of Aden? You may see the map below for the answer. List the first 3 layers of the atmosphere just above the Earth's surface. The answer is troposphere, stratosphere, and mesosphere. How did we prove that there is life deep in the ground? The answer is through scientific drillings. Jules Verne's famous book, A Journey to the Center of the Earth, reports how Professor Leidenbrock, his nephew Axel, and their guide Hans meet a versatile realm of living organisms on their descent into the interior of our planet. When the novel was first published in 1864, the idea of life existing in the deep subsurface, remote from sunlight and air, was genuinely science fiction. But towards the end of the 20th century, when scientific drilling opened the window into hundreds of meter-deep environments, it became clear that Jules Verne, in a sense, was right. What is the difference between evaporation and precipitation? Evaporation occurs when the physical state of water is changed from a liquid state to a gaseous state. Precipitation is the process that occurs when any and all forms of water particles fall from the atmosphere and reach the ground. Which one of these components, out of oceans and continents, occupy the largest portion of the surface Earth? The total mass of water on or near Earth's surface covers 71% of Earth's surface, 97.5% in oceans, 2.5% in glaciers, groundwater, lakes, and streams. Okay, let's now finally turn to the solid Earth. Solid Earth has a layered structure. These layers can be defined by chemical or physical properties. Chemical properties mean composition rocks and their minerals. Physical properties means deformability, differences between solids, liquids, and gases. Based on chemical properties, these layers are the crust, mantle, and core. Based on physical properties, these layers are the lithosphere, asthenosphere, mesosphere, the outer core, and the inner core. Let's add to this description some numbers to provide some perspectives on the volumes and masses of various layers. The crust has 1/250th, or 0.5%, of the Earth's mass. The mantle has about 2/3, or 67%, of the Earth's mass. And the core has 1/3, or 32.5%, of the Earth's mass. In other words, the mass of the crust is tiny compared to that of the core or the mantle. Similarly, in terms of volume, the crust is very small. The crust has 1/100th, or 1%, of the Earth's volume. The mantle has about 5/6, or 83%, of the Earth's volume. And the core has 1/6, or 16%, of the Earth's volume. Let's briefly describe layers of solid Earth resulting from their chemical compositions. The crust is the outermost compositional layer. There are two types of crust: the continental crust, which is up to 75 kilometers thick in the Himalayas, and the oceanic crust, which is 8 kilometers thick. Again, the continental crust is thick, up to 75 kilometers, with a mass density of about 2.7 grams per cubic centimeter. It is strongly deformed and quite old, maybe billions of years old. The oceanic crust is thinner, about 8 kilometers, with a mass density of about 3 grams per cubic centimeter, and it is comparatively undeformed and much younger, less than 200 million years old. This figure clearly shows large continental crust and a thinner oceanic crust. The mantle is the largest layer in the Earth at 2,900 kilometers thick, 82% of Earth's solid volume, and 68% of Earth's solid mass. It is composed of silicate rocks with abundant iron and magnesium. Its mass density ranges from 3.2 to 5 grams per cubic centimeter. The core has a central mass of about 7,000 kilometers in diameter, an average mass density of 10.8 grams per cubic centimeter, 16% of the Earth's solid volume, and 32% of the Earth's solid mass. It is composed of metallic iron. The lithosphere is the crust plus the upper portion of the mantle. It is a rigid solid. Its thickness ranges from 10 kilometers beneath oceans to 300 kilometers in continental areas. Thank you for listening to this iMode Education lecture. Remember, there is a large selection of iMode Education lectures, which can further enhance your knowledge of energy.